For our last day for our study of refraction, I want to look at a special case. This case is called total internal reflection. And you didn't hear me wrong. Even though this is a refraction case we're talking about, it's called total internal reflection because as light goes from a high index material, like this, to a low index material like air, sometimes it can bend so far away from the normal that it gets trapped in the incident material. Right at this point, total internal reflection occurs. This total internal reflection is not true reflection, like when light hits a mirror and bounces off backwards. It's not true reflection because it's not hitting a reflective boundary. It's hitting a boundary in which there's so much refraction that light hits the new material and basically gets repelled. The light is bending so far away from the normal line that it gets trapped in the original material. This is called total internal reflection, and the conditions for this mean that you need to be going from a slow material, like glass, into a fast material, like air. In fact, you should have noticed this in problem 1 on Thursday's homework, that at a 45-degree incident angle, going from glass into air, you don't get any refracted ray at all, just a reflected ray. Even though it's from refraction, it's called total internal reflection because the light ray does obey the law of reflection. An incident angle of 60 degrees leads to a reflected angle of 60 degrees for those cases.
So here are 3 good pictures to include in your notes. The first is just regular refraction. As light goes from a slow medium to a fast medium, in this case it's going from water into air, this red light would bend away from the normal line, making a larger angle, a fatter angle, in the faster material. In this case, theta I is smaller than the critical angle, and so this refracted angle is some number less than 90 degrees. It bends away from the normal line, but not so much so that it gets trapped. That's just regular refraction. Okay, so let's look at the extreme case. What if theta I is bigger than theta C? If I put it at too big of an angle, like with this yellow light over here, at too big of an angle, the light bends away from the normal line, so much so that it bends back into the original material and becomes trapped, creating total internal reflection. Now, with total internal reflection, even though this is a refractive property, we call this total internal reflection because in this case, it obeys the law of reflection. These 2 angles are congruent for anything above the critical angle. So, what is the critical angle then? The critical angle is the angle at which light goes from water into air, or from any slow material into fast, and it bends so far away from the normal line that it goes exactly between the boundary. The defining case of the critical angle is that the refracted angle is equal to 90 degrees. It's neither regular refraction, nor is it total internal reflection. It's neither of those. This is the critical case. At this critical angle, then it goes from then it goes from water and then travels along the boundary between air and water. So, definition for critical angle. This is the angle in the incident material at which light bends so far away from the normal line that the new angle, the refracted angle, is 90 degrees. When you substitute the critical angle into Snell's law in your calculator, it doesn't work. You can try to use ni sine theta sub I equals nr sine theta sub r. But when you substitute this into your calculator, you get an error. So let's show you how this works. So in this case, this is red light going from water into air. The critical angle in this case looks like it is about 50 degrees. I can tell this is almost the critical angle, but not exactly, because this refracted angle here is almost 90 degrees right here, but not quite. So let's see if we can find the critical angle for light going from water into air. The definition of the critical angle says that this is the angle in the incident material that causes the refracted ray to have a refracted angle of 90 degrees. So notice these two things I'm going to highlight in yellow right here. It's still Snell's law, but with a special change. At the critical angle, the refracted angle is 90 degrees. So let's try this out. It's going from water into air, so that's 1.333 sine something, I don't know what it is, equals NR, that's air, sine 90. And my calculator peeps, sine 90 is 1, so this is 1 is equal to 1.333 sine of the critical angle. So we're going to divide by 1.3 on both sides. And that leaves sine theta c is equal to 0.075, just about. And we're going to take the sine inverse on both sides to cancel out a sine. So imagine I'm putting a sine inverse here, S inverse, just because I can't write it. Making sure everything is in degrees, this gets us a critical angle as light goes from water into air of just under 50 degrees, 48.6 degrees.
So going back to this picture from earlier then, that means if I put in an incident angle of 30 degrees, well, that would be smaller than 48.6. 30 is less than the critical angle, so I just get regular refraction. If I put an angle of 70 degrees, that's bigger than the critical angle, I get total internal reflection. But if I put in exactly 48.6, then I get exactly 90 degrees out, and that's my critical angle. Your homework set for today is going to be practicing calculating and drawing regular refraction, total internal reflection, and the critical angle. But you're probably asking yourself, what sort of things is this even used for? Like, yeah, light sometimes goes through water and doesn't go through the air, like no big deal. But check out this picture I took. If we could get light in a denser material, so a slow material, to be trapped, we actually have the principle forming a fiber optic cable. The green light enters this plastic bent piece here. It total internal reflects off every boundary it hits, obeying the law of reflection each time until it shines out the other end. And this can be used to carry information across large distances, over extreme angles, and very quickly. It's one of the appeals of why we would use fiber optics to send signals. So, fiber optics have many uses. We use them to send information, and all we need is a high index of refraction material surrounded by a low index of refraction material. In this case, it's actually the water-air like we pictured during our little mini lab over there. Whereas the demos in the previous one were actually a plastic holding the light in. Another benefit is that, let's say I had a red beam at the same time. You could send two different signals and they wouldn't interfere with each other because they're different colors of light. This is just a cool video. In this case, laser light is going through a hole and is being trapped inside the water. The water is acting like a fiber optic cable with total internal reflection all the way down. So, for the last time, you're going into the PhET lab for bending light. Try your practice problems. As always, email with questions. Best of luck.